I'm assigning AirPassengers to my data. Now run it. Let's print out my data to see what it. So let's print my data to see. If we print out what is inside my data, we will assign AirPassengers to my data. So if you get something like this, have you done that? Okay. So now I can either plot my data straight. I guess it's because we zoom, that's why we are not seeing it. So are you able to get the plot at the end? Because I zoomed it. So now let's decompose. So to decompose, we use the function decompose. So now we have my, let's decompose without specifying which type of the model. Last week we talked about the additive model, the multiplicative model. So the additive model sum up the components. That is the trend, the seasonal, and the remainder. Either we call it remainder, residual, the noise. So the addition of all these components is the additive model. And the multiplication of all these components is the multiplicative model. So now we want to plot our decomposed data. So you should be able to get something like this. Okay, the code. So now let's specify each of the additive type, each of the decomposition type we want to use. Let's specify it as well. The last decompose we did, if you don't specify the type, automatically it uses the additive type. So the decompose my data one is just to illustrate how you can specify between the additive and the multiplicative type. Okay. Media. Okay, it's from there. I think it's from the media, so let's fix it. Where are we? Have you plot the decomposed? Yeah, okay. So now to specify the type of model you use. So what you have as in the decompose, let's call it decompose my data one. To decompose my data, comma size equals multiplicative. Okay. Because I'm changing it here. It's not showing on the screen. I've done that here. It's not showing on the screen. It's not showing. Will I be- So when you type it, run it, and let's plot it. Uh, I can see it here. Okay, the end. So if you want to choose the additive instead of the multiplicative that is there, just write additive. So by now you should have typed the line. So let's plot this. So now we observe that the heading of, are we plot? So let's plot it. Now we have the heading to be the composition of multiplicative time series. Unlike the previous one where we have the additive time series to be the heading. So have we done that? Okay, now it's possible you visualize each of the components. So let's look at the name for all the components. We have thread, seasonal, and random. Despite the fact that this random can be also be called the irregularity in the data, the noise. If we use any word other than that, it will give us error, or we use the remainder. So let's specify which one we want to visualize. Let's do the blend part. So you write the decomposed part dollar. So we want to pick the trend part, and it's possible for us to view what we have in our decompose so that we can know what we have inside the decomposed class. So we observe some things. So this is the random for each of the months. This is the trend for each of the months. This is the seasonal component for each of the months. And this is the observed $X. So we'll be able to specify which of the components we want to see. So firstly, you can decide to check to view the composed part so that you can know the component that is there. You'll be able to call out the component you want to visualize. So the same thing, I can do that for the seasonal part. Now for the seasonal part, so let's write decompose underscore my data one is seasonal. So we want to plot, visualize the seasonal part of the decomposed data. Are we together? So we can see. And since we didn't specify our X lab and our Y lab, that's why we have our Y has this label to be decomposed my data one. We can decide to change that. So I can have something like Y lab equals so you can see that there's a change. It's still the same. If you need any help, you can signify, people will attend to you. Someone needs help, a candidate thing. Please, I want you to go around, go into the sections to attend to people. The code. It's the same code we are working on. We are only visualizing the seasonal part. And what I did last is to specify the Y label. So now let's plot the last component. Y lab is the seasonal, or let's say seasonal component. X lab is time. Seasonal component. Y lab equals to seasonal component. Ensure it's been inverted comma. So now let's do for the random component. So can we also, so this is how to decompose. And like I said last week, this is a classical decomposition. It makes use of moving average. So we also have another decomposition I introduced last week, the STL. That is the seasonal trend using Loess. That is locally estimated scatter plot smoothing. So what that does is, the advantage of that one over this is, when you decompose with that, you also get the same result. But in this case, we have some bars telling us which one has the most effect, the component that is really, our data is speaking to, that is really affecting it. So that's what we want to do now. So let's call that my data STL. You can use any variable of yours from your hand, but I want to use my data underscore STL. So the functions to use for STL decomposition is STL. So you can see that there are pop-up, if you are seeing my screen, where we have X, comma, X window, X degree. So if in case you need any element to use, this one will just give you an idea of what you want to do. Someone is there. Okay. Have you run it with debut error? So now our data is my data. So if you run it like this, it will give you an error telling us that the S window, that is the smoothing window, is 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 not found, is missing. So we have different, we can either say periodic. We have S window of 7, of 30, depending on looking at the seasonal components. Okay, maybe if you look at your data, you can see that there is an occurrence of maybe in 7 days, in 30 days, or you just feel that there is it's periodic. If you look at our, if you look at, okay, we are unable to plot our data, you can see that it's periodic. So we can specify the S window to be periodic. So now if you run it, it's run at my own hand. Let me get the feedback from your hand. My data underscore STL, have you written that? Okay. The STL, my data, comma, the S window. Someone needs help. S dot window equals to periodic in inverted comma. This is the end. Okay, the ending. I've already moved into the ending. Okay, so if you have done this, let's plot the previous. It's returning error. It's not returning error at this time. So somebody should help me attempt to thing. So let's plot. Have we done that at your end? Let's plot the STL decompose part. So by now, I believe every one of us will be able to plot the STL decompose part. STL is seasonal trend using Loess, that is locally estimated scatter plot smoothing. On okay, let's introduce comments. So the Loess is the locally estimated scatter plot smoothing. So have you all seen the plot? Hello everyone. Are we having errors? Okay, we are able to plot it. Okay. The comment. Yes, I explained earlier that they both give the same thing, but the advantage of this one over the classical one is that we are able to know which component has more impact. And I said the larger the bar, the longer the bar, the lesser the effect it has. Yes. So if you look at this, unlike the classical one, we have the seasonal trend and random. Using random, they are the same thing. But this one uses remainder. So by the time you want to specify, you use the word each of the function is no shift. So if you look at this, the trend has the bar in the trend part is very small. So which means that this trend has much impact. The data is telling us there is trend in that data. So since I know that there is this data is showing us trend, more of trend. So if I want to forecast, I will actually go with ARMA model. This type of data works better with ARMA. But if the seasonal pattern is telling us there is a strong seasonality in this data, so we can use the ARMA model. Like I okay. People are not getting me. If you are not getting me, please let me see your hand. On this side, okay, let me come over again. Like I said the other time, the STL decomposition and the normal decompose, the STL and the decompose, they do the same thing. But this STL has much advantage over the classical one, because even if we have outliers, it works well with data with outliers. It also gives us visualization of us, showing us which of the components has much effect or what our data is saying. So if you look at this plot on the screen, you can see that the bar in the seasonal component and the bar in the remainder component are very long, which implies that they are less sensitive. So for the trend part, okay, this is the bar. Oh, sorry. This is the bar. You can see that it's very long, while this one is shorter. So this data is telling us that the trend component, there is bar at this end. See, these are the bars. Can we see? But the ordinary decompose is not showing us any bar. If you look at it, you can check your previous figure. Can we all see? These are the bars. But those at this end. That bar is at that end. Mouth. Okay. So these are the bars. Can you see? So sorry. So now if I want to forecast, if I want to forecast, since I know it's the trend component that is showing much, so okay, I should explain again in terms of the bar. If you look at this bar, it's long. Oh, if you look at this bar, you can see it's very long. Like I said the other time, that the longer the bars, the lesser the effect that is telling us our data has. So if you look at this bar, for the seasonal it's very long, and for the remainder it's very long. So our data is not talking much about seasonal and remainder. So that means it's the trend that is taking most effect. So if I want to forecast with this for this data, I'm going to use the ARMA model. We have facilitators that will come and take us through that, but I need to explain how you will be able to know which model to use. And also I said the other time that if it is the seasonal component that is more pronounced, there is a way you extract. That is the reason for extraction. There is the way you extract the seasonal part, and you now analyze it with your temperature, your rainfall. If you want to know the one that has most effect, maybe the temperature that is imparting the signal in your data, whether it's the rainfall, whether it's the humidity, any of your climatic variables, you'll be able to verify whether it's the humidity that is most pronounced. The remainder is the same thing as the randomness in the data, the noise, the irregularity in the data. Yeah. So this remainder cannot be explained by seasonal or trend. So that's why it's being classified as the remainder, the irregularity in the data. So are we good to go? Have you all seen this? Okay, the code. So sorry. So let's go to the code. Let's now. Sorry, ma'am, I'm coming, ma'am. Yes, ma'am. Yes. Sorry, ma'am. Seasonal arima. Yes. If it has short bar. Yes. So now, have you now be able to visualize the SLL, the composition plus? So now let's extract each component so that we can visualize each component on its own. Are we together? Are we together? What is happening? What is happening? Question. Okay. In seasonal. Yes. Like I said, the decomposition will tell us the nature of the data. What is, which one is having the most pronounced. So it will give us idea on which model to use if you want to forecast. Now I said if it is the trend that is more pronounced, you use ARMA model. And if it is the seasonal that is more pronounced, you use the SARIMA. Yes. So I said that there is a colleague of mine that will come and take us through that. But for this session, it's only the composition we are looking at. So we need to understand very well so that it helps us to know the model, the nature, which pattern is having, what pattern is our data speaking about. So now let's extract each component in case we want to use any of our components. So for this STL, locally estimated scatter plot smoothing. Locally estimated scatter plot smoothing. So let's first extract our. So now I want to extract the component of trend from the STL composition that we've done. And our STL composition is my data underscore STL. So now you can see that if when I added a dollar sign, it gave me some options. So now we click on the times dot series, you open a bracket, comma, your inverted comma, then so I'm having error, so let's go and plot to see the component we have. You can see how I'm doing it. I got an error when I use string, so which specify that I'm not picking the component very well. supposed to be there. I don't know what happened. So I had to rerun my STL decomposition again because it's not supposed. I was thinking it's trend, but I realized that it's trend. If you look at it, the name of your column, you can see that there's seasonal trend and remainder. So now let's plot our STL trend. It's too large because I've already seen. So you can see that I can decide to change the S label like the way we did the other time. So I have my Y lab. So the same thing applies to the seasonal part and the remainder part. So now let me give you that exercise. Plot the seasonal part and the remainder part. In the normal classical decomposition, we make use for the noise, we make use of random. But in STL is the remainder. Do we get that? Oh yeah, let's do it. Have we plot? Let's plot for seasonal and the remainder. So that will be all because the time is against us now. For the trend, we are able to extract this trend. We call this STL trend. The code. So like we have in line 15, do the same for the seasonal and the remainder. The seasonal and the remainder. Daddy, did you need it? Someone needs help. Another person needs help here. Please, let's attend to them. Someone is there. So, do we now have our seasonal plot? Yes. The remainder plot? Yes. How many people? If you have gotten your seasonal plot and your remainder plot, let me see your hand. I'm only having 3 hands, 4 hands, 5, 6 hands. Okay, 7, 8. Okay. What's happening here? Okay. I only have 1 person here. Are we following the class? Okay, okay. So in our lecture time, we can lay our hands on different data. So we didn't have all the time. We would have done some exercises. But this is how to go about decompose and STL decomposition. So thank you very much.